I'd like to welcome everyone to this afternoon's session of the celebration. Our first speaker this afternoon is Martin Grötschel. As you can see, he is a director and is involved in many institutes in Berlin. He's also a co-author of the book with Lovaas and Schreiber, Geometric Algorithms and Combinatorial Optimization. And he's going to speak to us today on the vehicle circulation from Hungarian.
Thank you very much, and thank you very much for the invitation. I just recalled it was 29 years ago that I first spoke in this building. There was 1976 when there was the International Symposium on Mathematical Programming. In those days I was still in Bonn, and then at Grötschel, my PhD advisor, advised me to go to this meeting here, and he was right. It was the best meeting I ever attended, and went to these meetings ever since. And I made a lot of Hungarian friends, of course, on the run during this time and later on. So I will speak about the use of the Hungarian method in public transport. And Jack already said something about the assignment problem, and I just wrote this a few moments before he spoke. It's a mathematical problem, and mathematicians have spent an awful lot of time to create real-life interpretations. They look like the assignment problem is useful, but I actually think it's not. It has no practical value in a sense. But the truth is, and this is what I find surprising, that's why I'm speaking about it, it's just the other way around. Practitioners have tuned the applications in order to be able to use the Hungarian method. And that I found very exciting, and that's what I will report about. The reason why the assignment problem is not really practical is that you don't have it in the pure form. You always have extra side constraints which you cannot amend to the problem. You have to look at something in addition. But you will see what is happening with the Hungarian method. So what is vehicle circulation or scheduling? I will explain this. Now here you have public transport. You have long distance trains, regional, local trains, streetcars, subways, buses, dial-ride systems and so on. They have to be planned, optimized and controlled. And that's a gigantic area for optimization. My computer just tells me that I have to give a talk. And here is what you usually come up in public transport planning. There are things that they call planning. This is long-term, service level, design of networks, line planning, timetabling. Scheduling is the usual way they use the name here for medium-term planning, where the target is cost reduction. And that's where vehicle scheduling comes in, duty scheduling, duty rostering. And then there is the day of operation business, namely dispatching. What happens if some bus driver gets ill, there's a delay, how do you manage that? So that's a gigantic area with huge problems. And the one I will speak about is the vehicle scheduling, one particular type of transport task that you can handle with mathematics. So I have a large number of people who have worked on this in this area, and the ones I want to mention particularly are Wolf Borndorf and Andreas Löbel, who have been working on this for quite some time. But we are covering all kinds of other aspects of public transport. And that is basically our activities. What you see here are codes that exist and that are marketed also. But I will not go into the details of that. We have two spin-off companies that came from our public transport activities, LBB and Intranets, who are doing successful business with the codes developed here. So let's go to the question, what is vehicle circulation and scheduling? So what we have now is a transportation system in some region. Somebody has designed it, it's there. And you subdivide it according to carriers or vehicle types. Say buses and trams are planned differently, subways, planes, ships. And for each carrier type you have a timetable. Then on this timetable are the so-called timetabled trips or scheduled trips. And you have a period of planning. That could be a day, like in public transport, a week, it's usually done in airplanes, or monthly if you plan ships. And the task is to assign the available vehicles to the scheduled trips of the timetable so that some objective function is minimized or maximized, and then you have additional side constraints. But in real life, you have to be much more precise. Namely, each vehicle has what they call a home base for a bus at some location where it can park. And so, in addition, what is a vehicle type? It may be exactly the same vehicle. If it's parked in a different area, it may be a different type according to the definition. So for us, a depot is usually a system or a set of indistinguishable vehicles that are parking overnight in the same location. That's what the depot is. So you have to be very careful with the definition. And then the vehicles leave in the morning, meaning it could be Monday morning and they come back home in the evening, and it could be Saturday night or something. And what you would like to do is a plan for every vehicle, its route through the planning period. And every scheduled trip has to be somehow on one of the trips, and you want to minimize something. So that's what the vehicle circulation problem is. And since the vehicles come back home, that's what they call it, circulation. And so the objective is to minimize the operation costs. But the vehicle circulation problem has several objectives. The main objective usually is the number of vehicles that are needed in order to cover all scheduled trips. I'll say a few words why this is the main objective. The second one they use is the minimization of the cost of the deadhead trips. A deadhead trip is a trip that is done empty by the bus. The bus comes from the depot to the starting position, it's empty, that costs. Then it ends up somewhere and the bus has to wait, that costs. And that's also a deadhead strip if it stands there. But sometimes they go from one end terminal point to another terminal point with driver, without driver, and you have costs. And you would like to minimize the cost. And that's usually a secondary objective. But then there are issues of interlining turns, pull-in, pull-out trips. I will say something about that later. So the whole thing is much more complicated than it looks at the beginning because they have parameters they want to tune, and we have collected the parameters they are using. It's about 200 that the company worries about, and what is a side constraint and what is an objective depends on the company. It's not so easy. Here is the reason why buses are so important. This is a study which is already 8 years old that says what is the annual cost of a bus in Germany. In urban transport, it was still in Denmark, it's 475,000, and in regional it's 300,000. The main cost is crews, and they specify what the cost is. And the basic result is that what costs are buses. If you don't have the buses, then the cost reduces. They want to minimize the number of buses, and you can keep in mind, in Germany at least, the annual cost of a bus, running a bus is between 150 and 250,000 US dollars per bus. And they somehow believe it's basically determined by the number of buses is the cost, and they want to reduce the number of buses. And so we have now optimized that, and we are now, for instance, in Berlin, all the buses, streetcars and subways are run by our system. And I have a little film I want to show. And I hope it works. Is it loud enough? And now this has been marketed, and on the left-hand side, so you see real users that are all over the world that are using our system to optimize their bus routes. So that's about vehicle circulation. And now I want to say something about single depot vehicle scheduling. So single depot means there's only one type of buses in one location. And there is what I call the depot in the morning and the depot in the evening. Of course it's the same, but I just split artificially into two pieces. That's the reason. And then I have a scheduled trip, say number 2, there's a starting time and location and an ending time and location. That's a timetabled trip. And what you see here is 4 timetabled trips. And that's what you want to plan. How do you go about? So now you add the so-called deadhead trips. And the deadhead trips are these additional trips that go from the morning depot to the initial position, or to that, and then intermediate from this one to that one, and you have to add them all as possible extra trips the bus has to take. And here are, for instance, 2 bus routes, the blue one and the red one. This takes a pull-out trip, goes to that does the scheduled trip, that does this trip, it's a deadhead trip, scheduled trip, deadhead trip, and goes home. That's the one single depot vehicle scheduling. And you can transform this into an assignment problem simply by multiplying the number of depot nodes. For each bus you have a depot node, and then you can just see this solution on the left here. Namely, the red tour is going from the depot of the red bus to 2, then it goes from 2 to 4, and then from 4 to the depot node, and that's exactly the same trip as here, it's just a different model. And that's the assignment problem that can be you can derive from this flow problem. And the only trick is you add 2 depots for each available bus, and then you have the assignment model of a single depot vehicle circulation problem. So it appears in practice. And in the 70s, they were actually using it. And they were reducing the multiple depot problem to one single depot problem, but they couldn't solve it. The computers in the 70s and 80s were just too small for the size of the problems that existed, and the codes were not good enough. But the Hungarian method was the method of choice. And when I first started working in this area, everybody in public transport knew the Hungarian method. I was completely surprised. You go to a traffic engineer and you tell him about, wow, we are solving vehicle circulation. Oh, you have a new version of the Hungarian method. That is the usual reaction. And here is one of the most successful projects. It's the HOT software, Hamburger Optimierungstechnik. What they did, they could not solve the whole day, so they looked at the peak hour, that is about between 6:30 and 8:30, and then they would solve the assignment problem for that piece of time, and the rest they would do heuristically. And so the assignment problem was a motor that was driving this software. And this software was developed in the 70s and was running until 2003. That were the last installations replaced by our systems, for instance. Here is the web page of HOT2, which we worked with these people. It's very difficult to find out what they really did, but I know exactly what they did, but nobody really tells you all the heuristic tricks. And the other companies that were running software for public transport did basically the same. And then in the end we made comparisons, and it turned out that for small cities, they actually found optimal solutions. Due to the enormous expertise they had, the knowledge and the tricks and so on, they were doing a really good job, but only for small cities like in Berlin or Hamburg that was not the case, because it's much too complicated. But I think it was a big achievement, and the Hungarian method was really the driving force there. And here is, and I taught it just 2 weeks ago to my students. Here is the Hungarian algorithm and so on, which I don't want to go through here. You know what it works, how it works. Okay. Okay, let's stop that now. Too much. So that's nicely to explain success and shortest path and so on. But what I wanted to say in the end, we have now replaced the Hungarian method by a very fast min-cost flow algorithm, which is actually has entered the spec suite and is affecting you, because all the hardware that is produced is using this suite to test how fast algorithms are. how fast the machines are. And they have a suite of 20 algorithms that are run, and they take the cumulative time that is used by these algorithms. And one of the algorithms is a min-cost flow algorithm, MCF, developed by Andreas Löbel. And so whenever some new hardware is designed and they want to make it fast, they are using a min-cost flow to test, so they get automatically faster. So that is very nice to have. That's the min-cost, that is the spec CPU 2000, and the next one will come out, CPU 2006, and the MCF code has also made it to the final stage, so that will stay there and the computers will get faster for our codes. But now let's come to the real stuff, namely multiple depot vehicle scheduling. So I mean, this is, for instance, the Berlin Metro bus network. These are the long-distance buses in Berlin. It's not the small regional ones. I just have a look at the many buses that are running around. So that's a gigantic system of buses. We have about 1,350 buses running in Berlin. Every day they have about 28,000 scheduled trips, and you have to connect them up in order to make a good design using a minimum number of buses. So the input here is a timetabled trips plus the deadhead trips. But somebody has to generate the deadhead trips. And in our case, it's about in the range of 100 million. 100 million variables, that means, and that is the size of problems that you have to solve. And if you reduce it, you can get it down to 70 million, but you still have something to solve. And now you can imagine why in the 70s even assignment problems couldn't be solved. They are really, really big. So you have vehicle costs and the depot capacities, vehicle types, and that is changing over time. They close down depots, they change the type of buses and so on. That's progressive work and changing all the time. And the output are vehicle rotations. And that's what I want to mention here, that it's very difficult to find out what is the real definition, because every company uses a different word. In one company it's a vehicle circulation, in the other vehicle schedule, in the third it's a block, in the fourth it's a rotation or schedule, and so on. And when you talk to the people, you really have to say, what do you mean by this? So that's why I'm mixing circulation, rotation, and schedules to get acquainted with this. It's all the same in my talk, but for the people in the companies, it may mean something different. It's not so easy. So the goals usually is minimize the number of vehicles and operational costs, but there could also be line hopping, and I want to say something about that. So the graph theoretical model is this. Now we have two bus types, the red one and the green one. It's a morning depot, R plus, and the evening depot, R minus, and these are the timetabled trips. And what you see is that certain trips can be taken by green buses only, some by red buses, and some by both. The green bus could be a double-decker bus that cannot go through some bridge, and you cannot use that in some line. So then you add the pull-out trips that come from the depot and the pull-in trips that go back into the depot for the red and the green ones. And then you add the deadhead trips, namely the trips that the red bus can do from one location to the other. Well, what you do not see here is the time dimension, because it looks like it goes backwards, but this is only the space, but there is also some time. And here's the green deadhead trips, and if you could put, and then in the end you put capacities on these arcs that go back from the evening depot to the morning depot. That gives the capacity of the garages. So that's a model that you come up with, and that's the end. This is the model that we are using, and that's I'm mentioning. This thing is the 100 million edges graph that you have to solve in Berlin. And here would be a solution. The red bus goes from the morning depot and returns as a red bus in the evening and not as a green bus, which is infeasible. Here is one picture of Regensburg where we are currently doing it, and this is only 1 hour of these buses, and these graphs are just not describable. It's not easy to make a picture. So the vehicle now, scheduling, now I'll explain some of those side constraints. So the pull-in trips, the way to minimize the number of buses is simply you put costs only on either pull-in or pull-out. So pull-in is getting started. All of the other costs are 0, and you have cost 1 on the edges, and if you minimize that, that was the minimum number of buses you want to use, period. So that's one thing. The next thing is interlining trips. So if that would be bus number 100, it's still 100, and that is 200 and 200, then going from 100 to 200 is changing the bus number. So there are companies that say we don't want this. Okay, then you penalize this, and others say we would like to have a change, and then you make it an extra cost. And then they say somebody who is on 100 wants to stay, but some guy who is on bus 300 only wants to do this once, and then he wants to change. And you cannot believe the number of extra things that come in, but you handle this by objective function. Turning trips, I will not go into that. Then there is something strange that we invented, is the pull in and pull out trips. So there is a bus that goes back during lunchtime and comes back from the depot, but it's not a real pull in or not a real pull out. You really need these trips in order to find the minimum number of buses. I will not go into the details of that as well. And then you have this depot capacities that you have to put soft upper limits and so on. How to model the soft limits is not such an easy issue, and the timelines I will not go into that. But what it comes up is, this is an integer programming model of multi-commodity flow. It's a multi-commodity flow problem, and that's the problem you have to solve. So that is this 100 million variable problem, and that's very easy. You can put it on one slide. The only issue is how you do that in practice. So the LP relaxation does not produce integral solutions in general. Problem is hard. There are actually, Eva Ptado showed that pseudo-polynomial time approximation algorithms to solve the LP relaxation, but I have not seen anybody use it. Eva, do you know anybody who is using this? We are still using integer programming, linear programming.
Using what?
Like approximation in practice. So we've tried it, but it didn't work for our practical purposes. So, and now you would say, what type of linear programming are we using? We are not using simplex method, and we're not using interior point methods. We are not using non-differentiable optimization. So that is a strange thing. Namely, we do a Lagrangian relaxation. Now it's simply splitting the problem, and it turns out, if you take out one of these, the problem gets easy, and you put it in the objective function, and then you try to look what methods are there around. And the one we have decided to use is a bundle method that has been developed by a couple of people. The main references are Kiviel and Helmberg, but there's Zove also involved and some others. And what you basically do is you make a piecewise approximation of the surface you want to minimize, and you have some theorems that go along. There's convergence. But in practice, that really is not the issue, because the convergence in theory is too slow for practical purposes. But you have to come up with some tricks to make this fact quickly converge. So, but the nice thing is a theory about, and this is a good method. There's primal approximation. You have to solve quadratic subproblems, which is non-trivial. So you have to bring in some quadratic programmers to come up with the best possible solution of the quadratic subproblems. And here's one example of how we tested which are the good methods. So this is one example of the 1 million variable problem. And we have compared the bundle method, the volume method, the barrier, and the something else, the casted method. And the bundle method turned out to be the most useful in practice. It's stable and robust, usually comes to a good solution, but you will never come to an optimum in practice. The barrier is very poor. You see the green line. And since Bill has shown a patent, here is a patent on the barrier method, which actually is called the interior point algorithm. I just mentioned at lunchtime, it's Karmakar's patent. And you are not supposed to use this interior point algorithm because ITMT has a patent and they're going to sue you if you are using this in real life. So that's why one calls it barrier. And since they are only using this interior, you make a polar transformation, interior goes to the outside, and you have an exterior algorithm, and they have no patent on that. So that's a trick how to get around. So we are doing Lagrangian relaxation, and you remember this. So what we do is we take the vehicle flow into the objective function and leave the rest. And what turns out, it's a min-cost flow single depot. Well, basically an assignment problem in a sense, a variation of that. So you need a very, very fast min-cost flow algorithm in order to solve the individual steps of this algorithm. And so the basic thing is to compute the gradients and so on, but the simple steps are very nice. And the other relaxation is of the same type, but now you can actually subdivide the problem into quite a number of independent min-cost flows. For each depot you have an individual min-cost flow. So we reduce the whole multi-commodity flow problem, the LP part of it, to a series of min-cost flow problem, and then govern this by a subgradient algorithm. I mean, it's called the bundle algorithm. And then you experiment with this. And I could give a 2 hours talk about how to really do this with the lambdas and so on. And you have to find out some real good tricks in order to make it work. But neither the simplex algorithm nor the barrier method is able to solve problems of that type. But here is a real advantage using nonlinear programming, and that's the machinery we have been using. And of course you need hundreds of extra tricks like heuristics, cluster first, schedule second, and the other way around, and reschedule and taboo search. We throw this all in, and that is successful. And I can even give you a show, but I think I don't have enough time, how the Lagrangian relaxation works, how you put in the parameters. Let me give you computational results. For the current system of BVG, that was the last timetable, we reduced it to 70 million variables, and we run this in 200 CPU minutes on a laptop. And so I think that's something significant if you can solve this in 3 hours or so on a laptop using this approach. And what can we prove? In the end, we can come up with the minimum number of buses that are needed to cover every trip in Berlin. And now, when you have the minimum number of buses, we go for the min-cost solution concerning the deadhead trips. And then we usually end with, say, 2-3% off optimality, because nobody cares for the last 2 or 3%. These are estimates anyway. There's no exact numbers. You are just estimating these. And then you look at the bus schedules, and then you see something like that. And that shows there are some buses that are not used at all. I mean, they're only going out for 1 hour, doing one trip and come back home. And that is due to the morning peak. And the number of buses is basically determined by the morning peak around 7 o'clock. And that's what the people already knew, and they were working on this to find good solutions. But when you have big cities like Berlin, you have not the same peak everywhere. In Zehlendorf, it's different from Wedding, and even in some places we have an evening peak. And then you can try to let the buses flow through Berlin, and you can get significant reductions. And I'm not allowed to tell you exactly how much we saved, but I'll show you some numbers soon. Here is, but I can get you the numbers from Bonn. We have optimized the SWB, the Bonn and Bonn system. There we save 5 of 200 buses. That's not that much, but this is a very small town. I mean, not everybody would believe that it's small, but from our point of view, it's small. And these are the slides that the Heiko Klotzbücher, the person in charge, gave me. This is the people who are doing this, Ralf Borndorf and Andreas Löbel, and we are now working on extensions of that. And the company that is distributing the software that they developed is Löbel, Borndorf and Weider. But here are the numbers that were saying that it was 100 million, okay, that somebody said they could save, and in fact it's more than that. If you look at the number of buses saved in Berlin, they were running with 1,850 buses 10 years ago, and now they have 1,300 buses, 1,350 buses. Now we are working on extensions of that, and I just want to mention 2 pieces of work very briefly. My time is running out. We are doing duty scheduling also, which I did not mention. But this is done in succession. First vehicle, then duty scheduling. What you really want to do is do this together. But this is an object where you have a couple of billion variables. Here you have a couple of 100 million variables. And putting this together as hopeless. But we are working with small cities like in Regensburg. We have been able to optimize that together, and that has some significant progress. And then we do the trip shifting trick. And the trip shifting trick we learned from the people in practice. They called it Sensi. In the German the word was Sensi. I said, what is Sensi? And it turns out it's sensitivity analysis. That's what they invented. The sensitivity analysis is simply this. They take a bus, and look, what that means here, the timetable of this bus is shifted a little bit. So he goes 3 minutes earlier or later. And if you do that, you can sometimes save a bus. Well, but you don't want to change the timetable. I mean, the bus goes at, say, 7, 7:15, 7:30, and so on. You don't want to make changes of 3 minutes. So the truth is they print the original timetable, but the bus driver has a different timetable. And people do not expect to be that they are in time. There's always plus minus 3 minutes or so. And then what they do, they did this iteratively, and we have now made a mathematical model of sensitivity analysis for such a system, so that we shift the timetable for the bus drivers, but not for the passengers. And we are saving quite a number of buses this way. And I think that's one of the tricks you can learn from practice. That's it, and thank you very much.
You have mentioned that there are 3 different kind of objective functions. The main issue is to minimize the number of buses, but the number of costs which is affected with your debt.
Dead trips.
Yes. So we are working for Hungarian railway company on some similar problem. And it's turned out that these objectives are contradicting to each other.
Yes.
So if you want to say what is better to have this kind of debt trips or to minimize the number of buses on a longer term, for instance a year or more, then it is not trivial how to compromise between the objective functions. What kind of experience do you have with this?
Yeah, so I did not tell you all the tricks and details, of course. So the usual thing is, that's why they want to have quick solutions. Number one, we compute the minimum number of buses, we know that's the lower end. Then they have reserve buses anyway. In Berlin they have something like 7% of the buses that are in addition to the ones they really need. And then they say, let's look at the interval of 5% of the buses and then look for the minimum cost solution within that. So we give an upper and lower bound on the number of buses and find a cheaper solution. And then they say, but we don't want to have this and that and that, and then you start playing with the parameters until the customer is satisfied. I mean, they are now doing it on their own, but the basic thing is you have 3-4 parameters they can play with, and they create something like 10 or 20 solutions, and in the end they sit down and decide which is the solution they want. And you were right, it's contradictory, so the minimum number of buses does not give you the minimum cost for deadhead trips. And if you look for the minimum cost for deadhead trips, you have too many buses, and so there's somebody in the end making a decision. It's not mathematics that decides.
One other question about the maintenance. If you schedule the maintenance of the buses, then it even makes larger the problem.
Yes. There are extra conditions. I have not told you everything. Like there are gas buses, for instance, in Berlin that only have a limited number of hours they can run. So you have to schedule return trips. And in a similar way, we schedule maintenance stuff. So you have extra, this was just a basic model. And the true model is extra constraints that you have to put in. And that very much depends on the company you are working for. This is a general model, and then you make implementations for the companies taking into account their special conditions that they have. But the whole system we have developed here can take care of that. So, but you can add linear side constraints in a limited number. I mean, it's not another 10,000 constraints or so, but if it's in the range of 100 or 200 extra constraints, we can handle that. Okay.
Any more questions? So can we thank Martin?